Hello everyone, I am going to work on this problem at your request. So step one for this problem would be to figure out how much total charge will be placed on the C1 just from this battery. So once that switch is closed, nothing in this branch matters since it's not connected. So this voltage will just be applied across the one capacitor, putting the maximum amount of charge on that one from that battery. Now that's as straightforward as it can be here. So for the charge on capacitor 1, that will be equal to the voltage of the battery times the capacitance of C1. Alright, and doing that, you'll get 46.8, not micro, millicoulombs. Alright, so now that's the total amount of charge that's going to remain on that circuit once the switch is flipped. Right, so that was all stored on C1. When the switch is flipped, all that's going to happen is the positives that were on this side of the plate and the negatives on there are going to start to move through the circuit. So these are going to try to follow that field and end up on that plate. These are going to spread out. Some of them are going to end up on that plate, right? Because those positive and negatives are going to try to attract to each other. Now, once those separate onto those two plates, that then polarizes the charges in that space. Okay? If we think through it that way, so this charge can only end up, whatever was on this plate can only end up on that, divide up onto that plate, and whatever's on this one can only end up and divide on that plate. So there's no new charges being placed along that whole conductor. That's just polarized. So what that does is that tells us these are in series. Right, so that's the first thing. We know C2 and C3 are in series. Because the charge of the C1 is going to divide over into this branch, that means this total amount of charge would have to equal the charge on C1 plus the charge on both of those. So if we have the total charge is equal to C1 plus, Q1 and Q23, whenever the charge is added, that's follows the rules of capacitors in parallel. All right. So now C1 is in parallel with the series capacitance of C2 and C3. All right. So total charge, and the charge is equal to just our old equation, Q is equal to CV. So on Q1 you'll have capacitance 1 times the voltage, and capacitance 2,3, that equivalent, times the voltage. Now I didn't subscript the voltage because C1 is in parallel with C23, and if they're in parallel, the voltage is the same. Alright, so QT, since the voltage is the same, we can take that out. So all we need now is to figure out what C23 is. Everybody has the same capacitors in the circuit, so it's going to be 1 over C23 is 1 over 6 plus 1 over 3, which is 2 over 6. So we have 3 over 6, so we get C23 is equal to 2. now we still have our C1, so for me it's 3.9. Everybody has 2 here. And we have our total charge from before. And a lot of times when you do these, the units will actually end up canceling out. So that's why I stopped writing them there. Alright, so what we don't know is the voltage across each branch. So when we solve for this, that's going to be the voltage across C1, and that's going to be the voltage across C23. Alright, so once we know the voltages across C1, we can just go back to Q is equal to C times V, plug in that voltage there, and C1, and figure out how much charge is there, and then figure out how much charge is on capacitor 2.3, the equivalent, using that voltage here, right? And since Q or C2 and C3 are in series, this amount of charge is on both of them. Alright, and I think that's it.